Picture this. It's late October 2026. Engineers at NASA's Goddard Space Flight Center are staring at a telemetry screen they've been watching for months. A number has just crossed a threshold nobody wanted to see. The Swift Observatory has dropped below 186 miles. The rescue window is closed. A $500 million telescope that spent 22 years rewriting what we know about the most violent events in the universe is going to burn in Earth's atmosphere, and there is nothing left to do. That moment hasn't happened yet, but it's where this story is heading, unless a robot with 3 mechanical arms pulls off something that has never been attempted in the history of human spaceflight. Right now, that robot is on its way to low Earth orbit. The margin for error is essentially zero. There is a way to stop this, but it requires catching a satellite that was never designed to be caught, using a spacecraft built in 9 months and launched from the belly of a commercial airplane. We'll get there, because that detail alone changes everything. And here's what the headlines are missing. If this works, it doesn't just save one telescope. It changes the rules for every piece of hardware humans have ever put into orbit, including the systems your phone, your GPS, and your bank account quietly depend on every single day. If it fails, we lose something we cannot replace and haven't planned for. In 2024, a team of astrophysicists were reviewing routine orbital data on Swift when they noticed something was wrong. The telescope's altitude was declining faster than the models predicted. They ran the numbers again. Same result. Something was pulling it toward Earth ahead of schedule. The cause was the Sun. Solar Cycle 25, the current 11-year activity cycle, peaked significantly stronger than any model had forecast. The surge of energy and radiation heated Earth's upper atmosphere and caused it to expand outward into space. On its own, that doesn't sound dangerous, but for anything orbiting in low Earth orbit, it's a slow death sentence. More atmosphere means more drag. More drag means more deceleration. More deceleration means a lower orbit. And lower orbits mean even denser atmosphere on the next pass. Swift had a design flaw that turned this into a crisis. When it launched in November 2004, Swift was built around one purpose: speed. Its mission was to detect gamma-ray bursts, the most energetic explosions in the universe, and pivot to face them within seconds of the initial alert. Engineers optimized everything for that capability. What they did not include was any propulsion system. Swift has no thrusters, no ability to raise its own orbit, no way to fight back against the drag that was slowly, silently pulling it down. From an original altitude of 373 miles, Swift fell to around 225 miles over 2 decades. That sounds gradual. It wasn't. Here's the physics nobody warned us about. As an orbit lowers, it enters denser atmospheric layers. Denser atmosphere creates more drag. More drag accelerates the decay. It's a feedback loop that compounds itself, and the lower Swift gets, the faster it falls. Mission managers ran the projections and got a number they didn't want. By mid-2026, a 50% probability of uncontrolled re-entry before year's end. By December, 90%. And there's a specific altitude that closes every option permanently, 186 miles. Below that threshold, the atmosphere is too thick for a rescue spacecraft to safely maneuver against. Scientists estimated that threshold could arrive in the fall, October, most likely. That's the deadline this entire story is built around. NASA could have accepted the loss. Instead, they called a startup. In September 2025, NASA awarded a $30 million contract to Catalyst Space Technologies, a small Arizona-based company. The mission: build a spacecraft capable of autonomously approaching Swift, capturing it without damaging its instruments, and boosting it to a safe orbit. The timeline they were given was 9 months. 9 months. The James Webb Space Telescope took more than 2 decades from concept to launch. Standard satellite development programs run 5 to 10 years. Catalyst had 3/4 of a year to build something that had never been done before, a commercial spacecraft designed to grab an active government satellite that was never built to be serviced, docked, or touched in any way. They finished it. The spacecraft is called Link. It weighs roughly 400 kilograms. 3 robotic arms extend from its body, engineered to grip a structural feature on Swift's outer frame. Xenon Hall effect thrusters will maneuver it to within arm's reach of Swift, then push the combined mass of both spacecraft upward to a higher, stable orbit. Engineers from Goddard worked through spring 2026, running Link through thermal vacuum chambers, vibration tests, and failure simulations. In April, testing was complete. Here's how it gets to orbit. Link launches inside a Pegasus 40 rocket, and the Pegasus doesn't launch from a pad. It hangs underneath a modified L-1011 passenger airliner called the Stargazer. The plane climbs to 39,000 feet over the Pacific Ocean. At a precise moment, it releases the rocket. The Pegasus falls for 5 seconds and then ignites, driving itself and Link into orbit. From there, Link spends 2 to 3 weeks closing the distance to Swift through a series of careful, incremental orbital adjustments, and then the arms reach out. Remember what we said, this has never been done, and here's the reason it's genuinely terrifying from an engineering standpoint. Swift has been in space for over 2 decades. Its external insulation blankets, the multi-layer protective wrapping around its structure, have endured more than 80,000 cycles of extreme heating and cooling as it crossed in and out of sunlight on every orbit. Those blankets may have become as brittle as glass. When Link's arms make contact, they cannot shatter what they're gripping. The capture must be firm and gentle simultaneously, and the entire operation must run autonomously because the communication delay between Earth and orbit makes real-time human control impossible. There is no pause button. There is no undo. Every decision Link makes in those critical minutes will happen without a human hand anywhere in the loop. There's one more threat nobody wanted to say out loud. The sun is still active. A major solar storm between now and Link's arrival could push Swift's orbit down faster than predicted, crossing the 186-mile point before the robot even gets there. The same solar cycle that created this emergency could end the rescue before it begins. Now let's talk about what we'd actually lose. Swift spent 22 years doing something no other observatory in the world could do: detect a gamma-ray burst and repoint to face it within seconds of the initial alert. Gamma-ray bursts are the most energetic events in the observable universe, the final collapse of massive stars into black holes, or the catastrophic merger of neutron stars so dense that a teaspoon of their material would outweigh a mountain. Swift detected more than 1,500 of them. In 2022, Swift was part of the team that recorded what astronomers called the BOAT, the brightest of all time. A gamma-ray burst so intense it saturated detectors across the entire solar system. The most energetic single event ever recorded from a cosmic source in the history of human observation. Swift was there. It was watching. Swift also confirmed that short gamma-ray bursts originate from merging neutron stars, a discovery that opened an entirely new field of astronomy and changed how scientists understand the life cycle of the densest objects in existence. There is no replacement mission in development. If Link fails, that capability is simply gone, but the consequences extend further than any single field of science. The Hubble Space Telescope is also slowly losing altitude. NASA has already rejected one commercial reboost proposal for Hubble. Today, the Hubble team is watching this mission with the kind of focused attention you pay when you understand your own future is being decided by someone else's experiment. If Link succeeds, it proves a concept the entire aerospace industry has needed proven. Aging satellites can be serviced commercially on compressed timelines by spacecraft built in months rather than decades. Think about what that unlocks. GPS satellites that route aviation, emergency services, and financial infrastructure, weather platforms that issue hurricane warnings, communications relays that billions of people depend on without ever thinking about them. Much of that hardware has no propulsion system. Much of it is aging. The question of whether it can be extended rather than replaced has never had a clean, demonstrated answer. It's about to get one. Remember the telemetry screen we started with? The number crossing the threshold, the window closing, the silence that follows. That moment is still in front of us. The airplane is ready. The rocket is loaded. The arms are waiting. Swift spent 22 years watching the universe destroy and recreate itself in ways we're still trying to understand. It would be a strange thing to lose it to something as ordinary as air. Which piece of space infrastructure do you think humanity can least afford to lose next? Tell us in the comments.